Hello everyone and welcome back to another video. Today we're going to be looking at simple pendulums and their generalized period. Basically, there's some assumptions you make when you look at the period of a simple pendulum normally, and some of those assumptions are false if you look at it generally. So yeah, first let's explain what a simple pendulum is. And a simple pendulum is basically just if you have so let's say that's the ceiling, you have a string, and you have a mass, and that's all it is. And basically with pendulums you usually displace it slightly, let's say to here, and then you release it, and then you watch it swing, which makes sense since it'll want to go to its lowest point, as you've probably seen in many science museums. So one of the things that's analyzed often in these kinds of simple pendulums is the period or its frequency. Basically, the period is how long it will take to swing back and forth, and the frequency is how many times it swings back and forth in 1 second. So basically, the period and the pendulum are related just directly by f equals t to the negative 1, since you have to measure, I mean, that should be fairly obvious. And basically, so let's first look at the normal way that the period of the pendulum is measured. So we're going to assume that it's displaced slightly by theta, and we're going to assume that theta is quite small. And this allows us to make some assumptions that make the differential equations quite nice for the oscillations. So let's consider the torque on this mass here. And let me draw it in solid because now we're analyzing it. Let me erase the mass and just draw the center line. And let's let the pendulum have length L and let it have mass M. So let's consider the forces on it. Obviously there's a force of gravity with magnitude mg, and there's also going to be a force of tension on this side pointing up like that. So if we look at the tension and we look at the horizontal forces and look at that, it gets kind of complicated because we have to know the magnitude of the tension. And basically the way we can get around that is by analyzing the torque instead. And analyzing the torque, we notice that the tension force doesn't matter since it points up along the string. So all that matters is this component of gravity. But one thing we can do more easily is, since it's just a cross product, it doesn't matter, we can take the moment arm, which is going to point like that, and that's going to have, since this is also theta, that's going to have magnitude L sine theta. So torque tau is equal to mg L sine theta. And basically with the small angles, we can assume sine theta is approximately theta. If you haven't seen this, we can just draw a picture here. If we draw the unit circle, so if we have a random angle here, theta, then we know the sine of this angle is just this height here. But we also know, since theta is going to be measured in radians, this length here is theta. So this length and this length, it's approximately the same, and as you get smaller, it's clear that they're going to be really close together. And for small angles, that's why you can assume sine theta is approximately theta. And replacing this side with I theta double dot equals mgl sine theta. Sorry, mgl theta, because we've made that assumption. And I in this case is just ml squared, since we're assuming it to be a point mass. I don't know if I mentioned that earlier, but a simple pendulum is just a massless string with a point mass. And it's not going to be a spherical mass, although it won't really matter if the radius is small. So we can cancel this entirely and make this a -1 and get rid of the m's. And from here, this is just simple harmonic motion. And this basically gives that the frequency omega, angular frequency omega, is root g over L. And so you can find that the period t is equal to 2 pi root L, sorry, wrong L over G. So this is the period right here if we make these small angle assumptions. And basically the angles start mattering when I think theta squared starts mattering, and for that won't happen until a while because theta squared drops off quickly for small angles. And so for that, so after that we can start, so now we can start analyzing the motion if it weren't for small angles, because that's a bit more interesting, right? This is really simple, a couple steps and we got the period. And also interestingly, you can get this through a dimensional analysis, except you won't have the dimensionless constant of 2 pi, but you'll still have a lot of information you need from right here. So now we're going to analyze the general motion of the pendulum. And to do that, we're going to try to find the velocity at a given theta, and using that we can find, so if we know the velocity at a given theta, we can integrate d theta over omega, where omega is the angular velocity. So we're going to do that by starting to look at this equation here, except we're going to get rid of this assumption here. And that basically tells us that theta double dot is equal to mg L to the minus 1 sine theta. And this is a differential equation in theta, and well, it's a differential equation in theta. And from here we can write d omega dx, dt, and d omega d theta dt is equal to theta double dot is equal to mg L to the minus 1 sine theta. And the reason we can do this is basically this cancels, or this is just chain rule as well, and this allows us to basically get a d omega and a d theta, and from that we can try to solve, because d theta dt is simply omega, right? So let's try to, let's move the things over, and this gives us a separable differential equation, right? And that means we can solve for omega as a function of theta, and we can integrate this value here. So we have the integral of omega d omega is equal to the integral of mg over L sine theta d theta. And one thing we can do is, instead of adding a integration constant, we can add make these definite integrals. And we're gonna start from the top here and go to the bottom. And if you go from 0 to omega to some speed omega, we can replace these with omega primes, and you do that as you go from the top angle, which is theta naught, is what we'll call it, and to some angle theta, and we'll just make these theta primes. But obviously that doesn't really matter since you can just do it. But this gives you omega as a function of theta. And we should note that if we want to actually solve this properly, we're going to want to add a negative sign here, because the angular acceleration goes this way and the theta is measured that way. So we want an angle, we want a negative sign so that all the signs match up, but that doesn't really matter to us. So but we'll go ahead and do that since that makes things easier. So on this side we get 1/2 omega squared, and that's going to be equal to, this negative sine theta is just cosine theta, so it's equal to mg over L times cosine theta minus cosine theta naught. And this makes sense since this side is positive, and for smaller theta, the cosine theta is going to be larger. So that cut off a little bit, and so now that we know omega is a function of theta, we can get this integral here. So let's write that down. And that integral was for the period, right? Since we're doing d theta and dividing by omega, this gives you dt, the small time. So t is equal to the integral from, let's just go from 0 to theta naught of d theta over omega which is equal to integral from 0 to theta naught of d theta over 2mg over L times cosine theta minus cosine theta naught, all square rooted. So we can manipulate this expression here. Well, by that I just mean make it a little bit nicer, and that gives us the square root. Oh, I don't know where the m came in. There should be no m here. Sorry. The m should have canceled out earlier, but my apologies. So it's going to be the square root of L over 2g times the integral from 0 to theta naught of d theta over the square root of cosine theta minus cosine theta naught. One thing I forgot to add here is that actually, since we're just going from 0 to theta naught, that doesn't give us the period, right? That only gives us going from 0 to theta naught. The period is if you have a pendulum here and it's here, it's going to go this way, and then come back. So it has to do the time it takes this motion 4 times, and so the period is actually going to be 4 times this, and this is our period here. So all we need to do is manipulate this integral here, and we're going to be able to figure it out. And we can make a clever substitution here, and both of these might not seem very motivated, but it's just doing math here, and I don't think anybody really cares about that. So the first substitution we're going to make is going to be using the half angle formula. We have cosine theta, so it looks like a 0. Cosine theta is equal to 1 minus 2 sine squared theta over 2, and similarly for theta naught. So that gives us that the denominator is 1 over root 2 minus 2 sine squared theta naught, theta over 2 minus 2 sine squared theta naught over 2. And from here we're going to make now a real substitution that actually affects so here we didn't actually substitute any of the variables like the integrating thing, we just used the trig identity. And from here what we're going to do is we're going to make the substitution sine x equals sine theta naught, sine theta over 2 divided by sine theta naught over 2. And this might also seem a bit weird, but it's because we have these here, and if you think about it, if we divide out that theta naught, then we're going to have a nice thing that turns into a cosine here, and that's probably going to cancel because this is a sine, and if we want it, when we're switching the integrating constant, the differential here, we're going to get the thing we want to cancel. So from here, let's differentiate this, and you'll get cosine x. So we're differentiating with respect to x. We get cosine x is equal to 1 over sine theta naught over 2, since that's just a constant, times 1/2 times cosine theta over 2 times chain rule d theta dx. So now we can substitute for d theta here, and we get d theta equals sine theta naught over 2 sine theta naught over 2 cosine x divided by cosine theta over 2. This cosine theta over 2 is a bit annoying, but we can actually solve for it using these, right? So dx. And so now let's plug in everything we have, and we have, so we're just going to work with this integral here, and we have that the integral is from 0 to theta naught of let me just write out all that here. So 2 sine theta naught over 2 cosine x divided by cosine theta over 2 dx. and we're going to divide that value by the square root of 2 minus 2 sine squared theta over 2 minus 2 sine squared theta naught over 2. And it's just a bit of manipulation here, and basically you'll arrive at the fact that this is equal to is going to be equal to root 2 times the integral from 0 to theta naught of 1 over cosine theta over 2 dx. And if you solve for this, right, using this, we're going to have cosine theta over 2 is going to be 1 minus the square of the product of these two. So that's going to be equal to root 2 integral from 0 to theta naught, oh that was ugly, over 1 minus the square root of 1 minus sine squared theta over 2 sine squared, so that should be sine squared x and sine squared theta naught over 2 dx. And we're going to use the binomial theorem here, and it's going to be equal to root 2 times the integral. Oh yeah, and this should not be a theta naught anymore, right, because we're integrating about x. And if we look at x here, when theta is theta naught, sine x is equal to 1, so x is equal to pi over 2. So pi over 2, pi over 2, pi over 2. So 0 to pi over 2, and doing the binomial theorem, it's going to be 1 plus 1/2 sine squared x sine squared theta naught over 2 dx. And which is kind of ironic here, we're going to make the substitution sine theta is approximately theta, and we're going to get theta naught over 2 squared. And so this integral looks a bit annoying, but one thing you can use is that the average value of sine squared x over any interval that's at over one of these kinds of intervals is going to be 1/2. So it's equal to root 2 times, so this is just going to be pi over 2, and the average value is pi over 2, so it's going to be pi over 2 times 1/2 times the value here, 1/2 sine squared x theta naught squared over 4. So now we just have this, and we just need to plug it into our value here, what our expression was here. And oh well, we notice the root 2 is going to cancel that, so this gives us, plugging this in, it's going to be t is equal to 4 times pi over 2 times root L over G from above times 1 plus, well, the pi over 2 disappears, so that's going to be 1 over 16. I don't know why there's a sine squared x here, so the average value of sine squared x was 1/2, so which is why we have 1/2 here, times theta naught squared, plus, well, that's it, but there's going to be extra terms, and we see this is actually 2 pi, and that's what we had earlier, 2 pi over g. And if theta naught squared over 2, theta naught is small, then this term disappears, and we get the 2 pi root L over g, right? And this is the correction that comes in when the pendulum gets larger. So this video is a bit mathy, but I thought it was pretty interesting to see how the period actually increases once you start adding in the corrections properly. And that's going to be it, and thanks for watching.